So to play around with this a bit, let's talk about some ARLs, some average run lengths for Shewhart X-bar charts. And in particular, let's talk about Shewhart X-bar charts for n equal to 5. Use any sample size I wish, but let's talk about sample size 5 here for a specific choice. Now, standards given limits for X-bar are, well, the lower control limit for X-bar is set at process mean minus 3 standard deviations for the process over the square root of 5, and the upper control limit is set at process mean plus 3 standard deviations of the process over the square root of 5. Pictorially, what I've got then is a picture like this. I'm going to draw for you here the probability distribution for the thing that's being plotted, in this case X-bar. I'm going to draw a normal distribution. I'm going to center that at the process mean, and this standard deviation for X-bar is the process standard deviation over the square root of the sample size, and as long as we're talking about samples of size 5, we're going to then be talking sigma over the square root of 5. And on this picture, there's the lower control limit for X-bar, here's an upper control limit for X-bar, and this distance here is 3 standard deviations for X-bar. This is 3 sigma over the square root of 5. Same thing, both sides of this thing here. What that means is that if all is well, and I mean by that if the process doesn't change, then this picture says that the probability that any X-bar value plots outside of control limits is just this area plus that area, and that means that this number Q is the probability that X-bar is less than mu minus 3 sigma for the process over the square root of the sample size, plus the probability that X-bar is bigger than mu plus 3 sigma over the square root of that sample size of 5. And what that gets me is that, well, if I rewrite this thing, X-bar less than that number is X-bar minus mu less than this. That means X-bar minus mu over sigma over square root of 5. That's less than minus 3. And this guy is somebody that I've been taught in Stat 231 to say is a standard normal variable, because I've taken a normal variable X-bar, subtracted its mean, divided by its standard deviation. Similarly over here, this is X-bar minus mu over sigma over square root of 5. which is a standard normal variable, is bigger than plus 3. And I've come to the come around to the very simple fact that this Q is probability associated with a z-value less than -3 plus the probability of a z-value bigger than +3. And if you look in a very good normal table, one that has probabilities to 5 digits rather than 4 digits, you'll find that that sum is about 0.0027. If you use an ordinary normal table, you'll get 0.0026 for that sum. I'd rather use this more accurate value, so let's just say that if I look this up online, or I use a very complete, a highly precise table, what I get is 0.0027, and that means that my average run length is this reciprocal of 0.0027. That turns out to be a fairly famous number, about 370. Okay, so the question is, what do I make of this? Well, that 370 says that if I set up an X-bar chart, everything is as it should be, then, and I start doing process monitoring, it's going to be about 370 periods on average before I get a false alarm. So, i.e., I'll typically wait, or I'll wait on average 370 periods to get a false alarm. Using the X-bar chart. So in some sense, this is a fairly conservative way to operate. I don't get many false alarms. This is a pretty good sized number, is what I'm saying here.